Hi, my name is Colin McCarthy. I'm a senior principal engineer. I work on EC2, our Elastic Compute Cloud, and I focus on Nitro, the system we're going to talk a good bit about today, and also encryption. And we're going to do a deep dive into AWS Nitro Enclaves, a new service that we've recently launched, and I know people have a lot of curiosity in. So I'm going to start actually with a bit of history, which is actually way back when I joined Amazon. If you looked at Amazon.com in the early 2000s, we were a very retail focused company at that time before our cloud offerings came along, and even at that time, we had developed this kind of core expertise in securing people's data, and that's because to process people's retail orders, we had to store their credit card numbers, and we had a lot of customers, which meant we had a lot of credit card numbers to store, and if any of those were ever compromised or revealed in any way, that would be just a really, really big deal for Amazon's business. And so we've always thought really, really hard about, well, how do we, keep information like that secure? And if you were to look at the architecture of Amazon in the 2000s, it would look something like this. We had a production network where most of our infrastructure resides. You'd have the web servers that were actually handling people's requests. You'd have backend systems that are doing some processing, figuring out if we have those books in stock and how many copies before we sell them to you. Databases, keeping track of everything. But we didn't store the credit card numbers there. Instead, we had a separate network we called the payments network, where we would store actual payment information. And then between the two, we had this really thin token service. And so when somebody added a credit card, we got into the payments network as quickly as possible, and it was assigned a token after that. And for all future references in the production network, we just refer to the payment instrument by that token, and never actually get the raw credit card number. And whenever we needed to issue a payment, the production network would kind of call into the payment network and say, please charge $20 to the following token. And it would go do that. And this is a very, very compartmentalized, very isolated network. That payments network was very limited in its functionality, very limited in its size, exposed a very, very small amount of surface area, and was very difficult to get access to. It had no internet access of its own, no interactive access. In fact, if you needed to do anything at all to administer that network, is quite a burden. You had to physically go to certain rooms that were connected to it, and you'd have to use specific machines that were already in those rooms. And this is a very classic information security pattern, right? Let's take our sensitive material, like credit card numbers in this case, but it could be any kind of personally identifiable information or health information or whatever, and just put it in this very isolated, secured network with a boundary around it, and let's be able to focus all of our paranoia and risk and control on any kind of thin surface area between those two. Very, very old pattern. And we still see this today as a pattern. In fact, it's a fairly common architecture that we see on EC2, where these days, because you can have things like virtual private clouds, you don't actually have to go build physically segmented networks like we did back in the 2000s. Instead, customers we can build all of this virtually, right? And they can have a VPC that is ring-fenced, has no internet access, has no NAT gateways. It's a very isolated network, and you store the sensitive material in there, and you do the processing in there, and you've got some kind of firewall between that VPC and then other VPCs where more general purpose things can be done. Very strong pattern, very very common to see. We've got customers who keep their own payment instrument, or well, their customers' payment instruments in private VPCs, or health data, like I was saying, or intellectual property, like sensitive machine learning models and so on. Very, very common pattern. But there are some, downsides and challenges with this pattern, right? It's kind of bulky. You have to build out these separate segmented networks and be pretty good about keeping everything separate. And there's some kind of inherent performance trade-offs, right? The traffic has to go between the public VPC and the private VPC, and you incur, at least a round trip on any requests that have to do that, right? And you've got the footprint of building all this out, right? You've got, instances in the private network, and you've got instances in the public network, and it's hard for those to share any underlying resources or costs. And so with Nitro Enclaves, we wanted to kind of take that, paradigm or pattern of like, well, let's be able to have separate environments for handling sensitive information, but kind of bring that down to the level of EC2 instances. And so the idea with Nitro Enclaves is that you've got an EC2 instance already, right? You can launch and run an EC2 instance, and you can pick from our, large variety of EC2 instance sizes that we offer, whatever best matches your workload. And then as long as it's a Nitro capable instance, what you can do with Enclaves then is then on that instance, launch and run a Nitro Enclave. And that Nitro Enclave is its own ring-fenced, isolated, compartmentalized, general purpose compute environment. And you can have actually one or more. And the model is that those general purpose compute environments kind of come from the instance itself. Like, so for example, you could launch an EC2 instance that has, let's say 8 vCPUs and 24 gigs of RAM. Well, you can say to Nitro, I want to run a Nitro Enclave. I want you to take 2 of those vCPUs and 2 gigs of my existing memory, and take that away from the instance, and instead, run a Nitro Enclave using those resources. And so the Nitro Enclave gets spun up, and it's provided there as a compute environment. It's actually a virtual machine. We'll talk a bit about that. And then anything can run inside that enclave. And the kind of threat model or kind of security model that we enforce is that, because of the Nitro system and because of the way it provides isolation and compartmentalization, the model here is that even if the EC2 instance is compromised or someone has unauthorized access to that EC2 instance, they have no ability at all to read the memory in the Nitro Enclave, to see inside the Nitro Enclave or see any material that's inside the Nitro Enclave beyond whatever the customer chooses to expose by virtue of running an application inside the enclave. We'll see that a bit more clearly later. But I just really want to emphasize this point, that we're not doing anything like nested virtualization or any kind of model where the Nitro Enclave is kind of running inside the EC2 instance. It's actually kind of running side by side with the EC2 instance, and Nitro provides a lot of isolation, and we'll see that. We'll see that in a bit. And besides providing customers with this kind of secure, trusted environment for sensitive data processing, it does a few other things. So it's as part of Nitro Enclaves, we're also providing integration with cryptographic attestation and integration with our key management services and our certificate management services, so that you can get material into an enclave or sensitive material into an enclave and actually then be able to process that. All of this the kind of way of interacting with enclaves or architecting for enclaves is that it uses an extremely convenient and familiar development model that's kind of as old as programming itself, which is that the way I think about it is you've got your main EC2 instance, a very general purpose compute environment. You can run anything you want on that EC2 instance. And with enclaves, you've got another general purpose virtual machine or compute environment. Again, you can run anything you want inside that enclave, but the difference is it's like they're connected by a virtual cable, right? There's just this one thin little cable between the two, and after that, there's extreme isolation. The enclave itself has no network access. It has no durable storage. It has none of the ancillary services that are provided towards EC2 instances. So it's extremely isolated and compartmentalized. So I kind of think of it like, well, I've got my virtual machine or my EC2 instance for doing general things, and then connected to it, I've got this other machine just connected to me by that wire, and it's connected to nothing else. And then with cryptographic attestation, we've got ways of getting material into the enclave so that it can be processed. And we'll cover that. All of this, everything I'm going to talk about in Nitro Enclaves, there's no additional charge for any of it, because Nitro Enclaves are created by essentially carving up resources from existing EC2 instances that a customer is already running, already paying for. There's no need for an additional charge, which gives a lot of extra agility. So before we get deep into how Nitro Enclaves itself works, we kind of got to build up and learn a little at least about how Nitro itself works. Because as the name kind of gives away, Nitro Enclaves are all built on the security of AWS Nitro. And to explain AWS Nitro, why don't we start with what things were like before AWS Nitro, or kind of without AWS Nitro, which is, in traditional virtualization, right? You take a physical machine, an actual server, the kind of thing you would have seen go into a rack, and virtualization is just taking that machine and using software and hardware trickery to make it appear to be, two or more machines that anybody can use. And this is what EC2 is built on. EC2 is a virtualization platform. AWS, we take physical hardware and we run virtualization on it, and then we're able to provide these instances for customers as virtual machines that they can run anything they want. And traditionally, you'd take that physical server, you'd run a hypervisor, which is the kind of software that powers that virtualization, and then you'd run a lot of other virtualization software there, things like virtualizing the network stack, giving every instance its own virtual network, the same for storage, for things like EBS, and then security and monitoring and management and all sorts of things like that. And if you looked at our, the virtualization platform we started with, all of this is running on one physical server. And we do a lot to make it very performant, very fast, reduce the overhead, but it's still all running on that one server. This is how a lot of other cloud providers still work today. This is a very kind of traditional picture of virtualization. Everything is sharing and running on the same CPU. All of that network and storage virtualization has to consume a bit of resources, and the kind of approach to security is, very traditional hardening of that software, lots of operational security measures, lots of things in place to detect if anything suspicious were ever to happen, lots of alarms would fire, all of that kind of stuff. That's what that world looks like. AWS Nitro is very different. So in AWS Nitro, we actually have two physical servers or machines. We have the traditional server hardware that customer instances are still running on, and there's a very thin hypervisor running on that machine, and it's an extremely thin hypervisor, because all it's really doing is, when the server boots up, it's saying, ring fence this memory and give it to this virtual machine for that customer, and so on. It's just doing some really basic interaction with the CPU's hardware-based virtualization extensions, to make sure everybody's memory is isolated from everybody else, and so on. That's kind of all that really needs to run on that machine. And then the majority of the virtualization and the security and the monitoring happens on the AWS Nitro card, which is actually a separate running system. It's its own server, effectively, that's kind of on a card, like a PCI card size thing, that's connected to the other machine. And so there's really strong, literally physical isolation between the systems. So the network virtualization, the storage virtualization, and the security management can happen on this separate, dedicated card. And there's a lot of benefits to that. Because it's running on a separate machine, it doesn't contend or have to fight for any of that CPU. So the customer gets all of the CPU that's available on the server they're running on. Because it's physically isolated, right? You've got a really hard boundary from a security perspective. It's a completely separate running system. It has its own physical memory, its own physical CPU. So straight away, a lot of potential security risks are just kind of off the table, right? Anything that could somehow exploit security issues in either memory or CPU on the server hardware no longer really have any path to impacting the virtualization system, which in turn means customers can be kept very well isolated from each other. And this whole system on the Nitro card, it's actually an AWS designed and built system. A division of AWS called Annapurna Labs designs and builds these systems, and that means we can put things in the card that we think make the most sense for our customers. For example, there's dedicated encryption and dedicated security functionality on that card that mean we can do a lot of the cryptographic work you're gonna see later in this presentation. And also, the way we architected the system from a kind of control perspective is that the whole thing is built using secure, encrypted, and authenticated microservices. There's no general purpose ability to log in to a Nitro card. There's no way for us to just ask a Nitro card to reveal to us customer memory or something like that. It's got all of these built-in controls based in hardware and software that prevent things like that. And the Nitro system is itself, an isolated and compartmentalized system that sits on what we call the EC2 substrate network and doesn't have general purpose access to the internet or anything like that. So that system is itself very isolated. And then because it's a standalone system, the Nitro system has an easier time, right, of verifying the hardware that customers are running on, right? An important part of security for the cloud, right, is making sure that things like the microcode and the BIOS and so on haven't been compromised, right? But if you ask a machine to verify itself, well, that's a very difficult problem. How do you know it's not being lied to by some functionality that's been compromised, right? Because this is a separate system, that problem goes away and is made far easier. I should say too that on Graviton 2 Nitro instances, which are it's another AWS designed and built platform, because we got the ability to design it from the ground up, all system memory is also encrypted on our Graviton 2 based instances. So we've got even more layers of defense there. Our strongest forms of control are actually that hypervisors just hard prevent memory from crossing between customers and so on. But we also offer encryption as another layer of defense. So that's kind of a grounding in the Nitro system, and hopefully that'll help us see how some of that translates into powering enclaves. So the model with Nitro Enclaves, just to go over it again a little, is you launch a Nitro-based EC2 instance, more or less as normal. There is a flag that you have to set to tell us, hey, I want to be able to run enclaves on this instance, but it's nothing special. Just launch an instance from the variety of sizes and types that we support. It does have to support more than 2 vCPUs because when you then go to launch an enclave using our Nitro CLI that we provide, you tell it, here's how many CPU cores and how much memory we want to dedicate to that Nitro CLI, and so, to that enclave. And so it does have to, at least have enough capacity to do that and have some left over for itself. And when you do that launch operation, when you say, hey, launch an enclave, you provide an enclave image as input. And so that image, it's kind of like a very small AMI, right, or Amazon machine image that essentially just encapsulates all of the software that you want to boot or run inside of the Nitro Enclave virtual machine. We provide some utilities to create those enclave images using based on Docker containers. That doesn't mean you need to run Docker or use containers in any other way to use Nitro Enclaves. It's just kind of a very convenient, nice, modern way to take a collection of software and turn it into an image. So when you run this, Nitro creates a new virtual machine. It does some attestation, and it runs the image, right? So we've got the Nitro hypervisor here, got the EC2 instance. We run the enclave. Now we've got 2 virtual machines where there was one before. And if you want to add more enclaves, go for it. Right? We actually only support 1 today, but we will be supporting more than one enclave in the future. And these enclaves, as hopefully is pretty clear from this diagram, they are peers or siblings or kind of side by side with the EC2 instance. And the separation between the enclave and the instance, or the enclave and another enclave, is as strong and hardened and well tested as the isolation between 2 EC2 instances is. So there's just no ability for them to read each other's memory or really see what's going on at all inside of one another. That isolation is enforced in hardware through a combination of the hypervisor will exercise those extremely well-tested CPU hardware virtualization extensions, which are very, very simple and in my mind makes them a lot easier to trust. Simply enforcing this virtual machine can't read these address ranges, this virtual machine can't read these other address ranges, and so on. Very, very, very simple. I spend a lot of my time working on encryption. I help write the encryption layers that we use at AWS, and to my mind, that kind of control where something is simply completely inaccessible and is not there is actually a lot stronger and more robust than something like memory encryption, where when all you're doing is encrypting memory, well, the size of that memory, the rate at which it changes, access patterns, all of that can be revealed. It's also very hard to do memory encryption in a way where it's not malleable and somebody can't just change some of the contents of that memory to try to do interesting things. All of those kind of difficulties and challenges that come with memory encryption, which also extend to using things like memory transactions, just kind of go away. You don't have to think about those at all in Nitro Enclaves. So we've got the Nitro Enclave running, right? It's got no durable storage of its own. It's got no network access, no interactive access. You can't just like SSH into an enclave. It's got no EC2 instance metadata service or DNS or NTP or anything like that. it is a very, very bare bones environment, very deliberately constrained. And then to match that, enclave images, certainly the ones we build and ship as examples and references, and our own enclave images for doing AWS functionality, are extremely minimal stripped down images. We're talking very, very small kernels with as little enabled as possible, very, very small user spaces with as little kind of utilities floating around, just to kind of match that very small compartmentalized profile that enclaves have overall. So we'll get those images up and running, and then to communicate between the instance and the enclave, we talked about that virtual cable earlier. What that actually is a thing called a VSOC or a VM socket. And this is not something we invented. VSOCs have existed and are used by as long as hypervisors have been around. They're just a convenient way for virtual machines to be able to communicate traditionally with the hypervisor, but here we're actually repurposing VSOC to use it to talk between two virtual machines. And a VSOC, you can kind of think of it like this local only version of TCP, right? It's like you can do TCP connections just between the instance and the enclave and vice versa. But it's a communication format that can't be leaked, spoofed, or intercepted, right? So it's not like IP where it could leak if some routing configurations are wrong or if some firewalling was wrong or whatever. This is secure and local only. It's very much like a cable. And but because you get that TCP-like interface over it, it's the kind of programming paradigm here, the way we architect for enclaves is, you just kind of treat it like, well, I'm going to run a process inside the enclave that does my sensitive data processing, and I'm going to use message passing or RPC or microservices or REST or whatever way I like to just ask it to do things, and then it's going to return the responses. So good example, like earlier we were talking about payments. You could say, make a request into an enclave that's like, hey, please charge the following amount of money to the following token, right? And then the enclave would go do that as part of its functionality. That's a simple example of a protocol. Inside the enclave, we do have a few other things. So we expose an entropy service to the enclave and an attestation service to the enclave. So the entropy service is just because this is such a constrained environment, actually the traditional mechanisms that kernels use to generate entropy, like looking at network and disk interrupts and so on, just don't apply. They don't work because it doesn't have a network, it doesn't have a disk. So instead we have a mechanism where the enclave can ask for entropy anytime it wants them, and we'll give it raw, cryptographically strong entropy from the Nitro system directly. And if it wants, the enclave can also use CPU-based entropy, so it can use the RDRAND instructions, for example, if it wants additional entropy from the CPU. And then the enclave can also, at any time, request an attestation document, right? And I'll walk through how attestation works for enclaves. So when an enclave application boots or something runs inside the enclave, it generates a local kind of public-private key pair, and those the private key at least never leaves the enclave, and these keys live and die with that enclave, right? When you terminate the enclave, they're gone, and they exist nowhere except in that enclave for however long that enclave is running. And the enclave takes the public key and optionally a nonce, so that's a number used once, something you need to use if you need to build anti-replay mechanisms into a protocol, and can provide those to the attestation service, right? So it makes this hypercall and says, here's my public key, here's a nonce, send me back an attestation document. And that attestation document will have a bunch of things in it. Well, first it'll have the nonce and the public key that the enclave supplied, but it will also have things like the checksum of the enclave image that's running, the checksum of the kernel, its application. It'll include the signature of a key that signed the enclave image. It'll include things like the instance that the enclave is attached to, the instance role, when it was launched, what the current time is, all of these kinds of things. And that document is then signed by us, signed by the AWS Nitro system, right? So that it can't be spoofed or forged in any way. And the PKI system that we're using to power that attestation is public. So anybody can verify these documents. Anybody can look at the signature in that document and verify, according to Nitro, only this kind of enclave could have possibly, received that attestation document, right? With that checksum or that signing key or whatever. And so using this, right, this document is very powerful and can then be used to kind of get material into the enclave, right? And the way to do it is, well, there's a few ways to do it. One way is to, well, let's just, so that the enclave can kind of let out that document, can put it out onto the instance, and the instance can use it to, ask for some material, and the material will come from some service, and the service should verify that, the attestation document is what they think it should look like, and the signature is correct, or the checksums are what they want them to be, and so on. That a particular enclave image is being run. And then the server can go, okay, well, all of that passes, so I'm going to encrypt material to that using that public key, and I'm going to send it back to the enclave, and the instance can relay that information. And that works, it's secure, that's called end-to-end encryption. The instance, even though it's passing messages around, never knows what's inside those messages because they're all encrypted. So that's one way. Another way is to use SSL or TLS. I'll cover that shortly. But we've actually kind of shrink wrapped all this for you, and we have first-class support already with both our key management service, KMS, and our certificate management service, ACM, where an enclave can actually authenticate to KMS using just the ordinary, protocols that we use to talk to KMS, but relayed via a helper agent that's running on the EC2 instance, and it can get back key material or decrypted material from KMS very, very conveniently for that. So we have that working as well. We've got strong examples of that in our reference images where you can see that in action. But the way to think about this in your head is, okay, Enclave publishes a public key that's been attested by Nitro, and then we send back material that's encrypted under that public key. Okay, so that hopefully pretty simple to get your head around and to use. In terms of the security model here, AWS takes all responsibility for the isolation between the instances and the enclaves. That's kind of on our side of the shared responsibility model. The way we do that, it's both hardware-based security, all that isolation I talked about in the Nitro system, and operational security, but then customers have to take responsibility for all the security of their applications. So if the customer is running an application inside the enclave and it exposes some functionality over the VSOC, well, then customers have to make sure that that functionality isn't itself vulnerable to something like a remote code execution vulnerability, or that it also doesn't have any measurable side channels in it. So a good example there is, if I give the enclave a certain input, encrypted input, foo, and it takes 5 seconds to process it, and I give it another encrypted input bar, and it takes 10 seconds to input it or to process it, then obviously from the outside I can tell which kind of input it got just by measuring the processing time, right? And so it's the customer's responsibility to be careful about things like that. But hopefully that shouldn't be too hard. And so let's go through some examples of how all this would work, right? So the most common example, how can we use a Nitro Enclave to do some sensitive data processing? So here, the way to think about it is, all right, you build an Enclave image that actually does your sensitive data processing. It's got an application in there that does something like, I don't know, let's look at a table of patient health information and count how many people have a certain disease, because you're interested in tracking that, like we all are with COVID right now. So the way you do that is you look at the application, you audit it, you vet it, you make sure that that's it, the code only does what you want it to do, and then you compile that into an enclave image. And when you build that image, we give you a set of, we'll tell you, here's that image's checksum. Here, you get to sign that image as well if you want. And then you would have your patient information encrypted under a KMS key. So that patient information could be in a database, could be on S3, wherever, but either way, it would be encrypted under a KMS key. And you'd put a policy on that key that says only an enclave that either has the matching checksum or the image signing key that you're comfortable with can ever use that key, right? And so when the enclave launches, it retrieves the data it wants from S3 or Dynamo or wherever, using the EC2 instance as a helper, and then it decrypts again using KMS and the instance as a helper to decrypt that sensitive information, and now it has the plain text and can actually process it. And then, release whatever results are considered safe to release, like the count of how many people have a disease, but not who has that disease. It's a good example of compartmentalized information control. The reason why we support both, you can either use the checksum or you can use the signing key is, if you really want to be hyper vigilant about saying like this specific image and only this specific image can have access to my data, then that's what the checksum is for. You can be that precise. But a challenge with that is every time you build a new image, well, the checksum will change and you'll have to add that to the KMS policy, right? And so for flexibility, some folks prefer, no, I'm just going to pin to the signing key, and I'm just going to have an application signing key, and I'm going to use that every time. And I trust whatever processes that I have in place to make sure I'm only going to sign good images with that key. So that should be pretty, that gives you, more flexibility. We have our own enclave image that uses all of these patterns. It's actually ACM for Nitro Enclaves. And so this is an AWS built image. It's open source as well, so you can see how we built it. You can copy all of our techniques to get going quickly. And what ours does is it actually uses everything I just said to retrieve an SSL certificate and a private key from ACM. So customers can go and create these free certificates in ACM for domains they own. And now with this Nitro Enclave image, it'll actually download it from ACM, decrypt it using KMS and the techniques I just said, and then it basically acts as like a little TLS offload engine for your EC2 instance. And so you can actually now terminate TLS and SSL on an EC2 instance using an ACM certificate and key, and the key never leaves the enclave, right? So it's a really strong example of using an enclave for sensitive data processing. In this case, the sensitive data is that SSL key. And actually, even if you've no broader interest in using Nitro Enclaves, this is really useful on its own. Just a great way you can use ACM certificates on EC2. So another example is where you want to do multi-party collaboration or multi-party computation, as parts of this are sometimes called. So a good example here is, you've got two businesses, each with a set of customers, and they want to find out how many customers that they have in common, right? And but they don't each want to give each other their full list because they don't really trust each other not to steal, the full list. And so the way a problem like this would be solved is, well, you write an enclave application that takes two inputs, Alice's list of customers, Bob's list of customers, and figures out what the intersection of those data sets is and releases them. And each customer, so let's say Alice and Bob in this case, they look at that image and they validate that application and they say, yeah, that application only does the things I'm comfortable with. I'm happy about that. And so Alice then takes her data set, her long list of customers, encrypts that under a KMS key. Bob does the same. And then they each create a policy that says, look, only that enclave that previously I've looked at can ever decrypt those data sets. And at that point, it actually doesn't matter who runs the enclave. Alice could run it, Bob could run it, anybody else could run it. Either way, only an enclave image running on a Nitro system will be able to produce an attestation document that matches that policy and can actually retrieve the keys from KMS and decrypt the material and do the operations that they both trust. A third example is for protecting intellectual property. So sometimes it's not the data sets that are as sensitive as things like machine learning models that customers can have invested millions and millions of hours of computation into refining, and so consider it a really, really important business asset. And for this case, it's actually really similar to the sensitive data processing case. The only difference is instead of just encrypting the data set, we encrypt the application or the machine learning model itself. So we create like a small stub enclave image, and all it does is kind of retrieve the encrypted application to then go and run. And in that way, the IP is fully protected. So hopefully with those three examples, you get those are, there's some really strong primitives, right, that we can build very agile and flexible applications on top of. Our work on Nitro Enclaves is open source. So the Nitro utilities, the agent, everything we're using to build our own enclaves is all open source, all available on GitHub. The kernel modules and extensions we've written for the Linux kernel so that the instance can run an enclave are also open source and already contributed upstream into the Linux kernel. Those modules essentially help Linux kind of offline the original memory or vCPUs that are donated to the enclave. They kind of help the kernel go, well, I was booted with 24 vCPUs and 20 gigs of RAM, but now I only have 22 vCPUs and 18 gigs of RAM, and kind of make it okay with that. They're just coordinating that little dance with the Nitro system. None of the security of Nitro Enclaves actually depends on anything that's running in the Linux kernel. It's just there for that coordination. But you can find all that on GitHub, on the Linux kernel mailing list, and so on. So this is all built on open interfaces, and in fact, you could take that work that we've put in the kernel. You could take things like our enclaves, and it'd be possible to build all of this over again and make it run even not on AWS, on-prem or wherever. The only difference would be that at that point the security wouldn't be being provided by the AWS Nitro system. It would be being provided by whatever's running all of that. Hopefully you've gotten some takeaways from this, but the biggest ones I want to emphasize are we're providing a very secure, very trusted environment for sensitive data processing. It's built using the Nitro system, but it's also a very convenient and general purpose environment. Unlike other enclave technologies or trusted execution environments or confidential computing environments that you may have seen out there, Enclaves doesn't require you to, do major re-architectures that require understanding things like, CPU models and memory transactions and memory barriers and so on. You don't have to think about any of those with Nitro Enclaves. Instead, you get to treat it with an extremely familiar model that should be productive for development teams who are used to building applications that run on the cloud. And that's all open source. There's reference patterns, ready and waiting to build on top of. And And to power all this, we've got some day one first class integration with KMS and ACM to get things running. So it's pretty, quick to get to a point where you can get some sensitive material actually into the enclave. Thank you for listening. That's everything I had to cover. If you've got questions or comments, we'll be able to take them.